In the vast timeline of Earth's history, there are chapters so surreal and extreme that they challenge everything we know about survival, climate, and the resilience of life. Among those forgotten epochs, one stands out like a frozen scar across the memory of the planet. There was a time when Earth itself became a prison of ice. From the deepest oceans to the highest mountain peaks, from the equator to the poles, everything was sealed beneath a crushing white silence. Nothing like this has happened again. It was as if the entire world had been turned into a colossal snowball drifting silently through the void. This ancient and haunting period is what scientists now call Snowball Earth. Not just a poetic title, but a literal one. The surface of the planet, they say, was locked under sheets of ice several kilometers thick. The oceans froze over. The continents vanished beneath glaciers. And sunlight, the lifeblood of our world, could barely pierce the blinding crust of frozen water that wrapped around the globe like a shroud. But this wasn't the result of a single winter, nor a temporary ice age. This freeze lasted millions of years, and the terror of it wasn't just the cold, it was what it meant for life, for survival, for the very possibility of the planet continuing as a living world. How could anything survive when the sun itself was reflected away, and when the seas home to nearly all life were no longer liquid? To understand just how close Earth came to losing its spark, we must go back far into the past, not just thousands of years, not millions, but over 600 million years ago. Long before the age of dinosaurs, long before forests, long before any creature had yet crawled onto land, back to a time when life was simple, microscopic, and mostly hidden beneath the water's surface. Back then, the planet was already old, but life was still young. It lived in the oceans, in tiny forms barely more than bubbles, fragile, primitive, yet persistent. These early organisms had already survived billions of years of change, from toxic atmospheres to meteor strikes, but nothing prepared them for what was about to come. Something shifted in Earth's balance, something invisible, but catastrophic. It began slowly, almost silently. Temperatures dropped. The ice caps at the poles began to grow. That in itself wasn't unusual. Ice ages had come and gone before. But this was different. The cold didn't stop. It spread outward. It consumed the continents. The oceans began to freeze from the top down. The sun, still shining in the sky, no longer warmed the Earth. Its light bounced off the growing sheets of ice, back into space. And the more the planet cooled, the more ice formed. A deadly loop with no natural stop. This was not a seasonal change. It was a planetary plunge into deep freeze. The equator, where temperatures today are sweltering, may have seen snow and ice thicker than the glaciers of Antarctica. And as the world froze, life faced a crisis of unimaginable scale. The oceans, once teeming with microscopic life, were covered with a solid lid of ice. Sunlight, essential for photosynthesis, was cut off. Ecosystems collapsed, and what little oxygen was in the water may have been trapped beneath the frozen shell, far from where most life could reach it. It was a silence that stretched for ages, millions of years of deep, suffocating cold. From space, Earth would have looked like a marble carved of white stone, drifting silently in orbit around the sun. Lifeless, frozen, forgotten. Yet something survived. Deep below the ice, near cracks in the sea floor, life clung to warmth. In places where the crust split and magma hissed into the dark water, hydrothermal vents spewed heat and minerals. There, in those shadows, were pockets of hope. Life that needed no sunlight, only chemical energy. Archaea and bacteria evolved to endure conditions that would kill nearly anything else, held on in the darkness. But even this wasn't guaranteed. The ice could have grown too thick. the gases in the atmosphere too thin, the oceans too stagnant. It was a race against time, where the future of all life on Earth balanced on the edge of extinction. And still, through all of this, the planet turned. It waited, slowly, unseen and unheard. Pressure built beneath the crust. Volcanoes began to stir. And with each eruption, carbon dioxide filled the air once more. Greenhouse gases, trapped beneath layers of ice and stone, started to tip the scale back toward warmth. But that is a story for later. For now, in this first chapter of Earth's most terrifying winter, we stand still at the brink of a frozen apocalypse and ask the question that echoes through time: how close did life come to vanishing forever? The Snowball Earth theory began as a bold idea, one that many scientists found hard to believe at first. The thought that Earth, in its entirety, could freeze from pole to pole sounded more like science fiction than geology. But over time, with more evidence gathered from rocks, sediments, and ancient fossils, the idea began to solidify. Today, it stands as one of the most extreme and fascinating explanations for how dramatically Earth's climate can shift. So, what is the Snowball Earth theory? At its core, it proposes that several 100 million years ago, the planet experienced one or more episodes of near-total glaciation. During these episodes, ice sheets extended from the poles all the way to the equator. Vast oceans froze over. Continents disappeared beneath glaciers. And the average global temperature may have dropped far below freezing for millions of years. This theory wasn't just created from imagination. It came from rock layers. Scientists found strange formations of glacial debris in places that, today, are tropical. Ancient rocks in Africa, Australia, and South America contain signs of glaciers, massive flows of ice that carved and scraped the land right near the equator. Such formations shouldn't exist in these regions, unless the entire planet had been much colder than it is now. And then there were the cap carbonates. These are unique layers of limestone that appear right above glacial deposits. They formed rapidly and globally, suggesting a sudden shift from deep freeze to intense warmth. The only way such deposits could form was if the oceans had been covered in ice and then quickly melted, releasing trapped carbon dioxide and minerals into the water. It was a geochemical fingerprint of a planet that had been frozen solid and then thawed in a burst of heat. But how did scientists tie all this together? It started with a puzzle. During the Neoproterozoic era, around 720 to 635 million years ago, there were at least two major glaciations. They were long, widespread, and left behind global signs of ice. Researchers studying the rock layers from this period noticed patterns that didn't fit normal ice ages. The deposits were too thick, too widespread, and too far from the poles. It was as if the entire planet had been locked into a deep freeze. This led to the development of the Snowball Earth hypothesis. It suggested that a runaway climate effect had taken place. Ice formed. It reflected sunlight that cooled the planet further. More ice formed. And the cycle continued. Without enough greenhouse gases in the atmosphere to trap heat, the planet spiraled into a frozen state. The oceans, cut off from the sky, lost their ability to circulate and exchange gases. Life was trapped below the ice, and the world became a snowball. But the theory also includes an escape plan. Volcanic activity, still active beneath the ice, would continue to release carbon dioxide into the atmosphere. Normally, this gas would be absorbed by weathering rocks or the oceans, but with everything frozen, there was no way for the gas to be removed, so it built up over time. Millions of years passed, and the carbon dioxide levels reached extreme highs. Finally, the greenhouse effect kicked in with overwhelming force. The ice began to melt. The Earth warmed rapidly. And life, barely holding on, emerged into a planet transformed by fire and water. The Snowball Earth theory not only explains a unique period in Earth's history, it also challenges us to think about the fragility of climate balance. It shows how small shifts, over time, can lead to massive consequences, and it reminds us that our planet, while resilient, is not immune to collapse. Even today, some parts of the theory remain debated. Not all scientists agree that the planet froze entirely. Some believe a slushball Earth is more likely, where equatorial oceans remained partially open. But the core idea, a global glaciation that nearly wiped out all life, is widely accepted as one of the most extreme climate events in Earth's history. In understanding this theory, we unlock not just the story of a frozen world, but the incredible resilience of life itself. A world where microscopic organisms waited in the dark, surrounded by ice, for a second chance to grow, evolve, and one day take over the planet once again. The idea of a frozen Earth wasn't born from theory alone. It came from rocks, from the language of minerals, and the scars left behind by ancient glaciers. Scientists didn't begin with a vision of a snowball planet. They began with questions, strange rock layers, misplaced evidence, clues buried deep in Earth's crust that whispered of an impossible past. It started in the deserts of Africa, the mountains of Canada, and the jungles of Australia, places that, today, are warm or tropical. Yet in these unlikely regions, geologists found unmistakable signs of glaciation. Huge boulders embedded in fine-grained sediment, rocks scratched and grooved as if dragged beneath a sheet of ice. Layers of tillite, ancient, compacted glacial debris spread across vast distances. These formations looked exactly like those created by modern glaciers, but they were found near what would have been the equator during the Neoproterozoic era. Based on the alignment of ancient magnetic minerals within these rocks, scientists could tell that the land had been located close to the equator when the glaciers passed over it. This was a paradox. How could glaciers exist where the sun's heat should have been strongest? At first, the idea seemed absurd. Maybe the continents had simply moved. Maybe the rocks had been misinterpreted. Maybe the data was wrong. But as more discoveries came in from all over the world, the puzzle grew clearer. These glacial signatures weren't isolated. They were global. And they all pointed to the same narrow window of time between 720 and 635 million years ago. Then came the cap carbonates, another mystery. These thin, strange layers of carbonate rock sat directly above the glacial deposits, and they were unlike anything else in the geologic record. Their presence was sudden, their formation was rapid. They suggested a massive chemical shift in the oceans immediately after the glaciers receded. Carbonates usually form in warm, shallow seas, where sunlight and life are abundant. But here they appeared right after a global freeze. And they weren't local. They were found across multiple continents, on top of glacial rocks that had formed near the equator. The only way this made sense was if the world had gone through a sudden, catastrophic warming event after being locked in deep freeze. These discoveries, equatorial glacial rocks and cap carbonates, became the twin pillars of the Snowball Earth theory. They were physical proof of a world gone cold and then abruptly thawed, but scientists didn't stop there. They looked deeper into tiny crystals called zircons, which could be dated with extreme precision. They studied the isotopes of carbon and oxygen trapped in rocks, revealing the changes in the planet's atmosphere and ocean chemistry. They examined banded iron formations that reappeared during these glaciations, suggesting that the oceans had become anoxic, lacking oxygen and rich in iron once more, conditions not seen since the earliest days of life. Sediment cores pulled from ancient seabeds told the same story. Layers of fine mud interrupted by massive stones, called drop stones, which could only have been carried and dropped by icebergs into the ocean. These layers showed that glaciers had reached the sea, carved icebergs, and floated across open waters before melting and dropping their rocky cargo. And perhaps most haunting of all were the fossils, or the lack of them. During these snowball periods, the fossil record nearly disappears. Life, once scattered in the oceans, seems to vanish. It's a biological silence that matches the geological chaos, and it speaks of a crisis on a planetary scale. Together, all of this evidence painted a chilling portrait of Earth, not a slow cooling or a regional ice age, but a rapid descent into a frozen prison. It wasn't one discovery that changed everything. It was the overwhelming weight of many. Each piece confirmed the next. Each layer of rock echoed the same terrifying truth. The Earth had once become a snowball, completely or nearly so. The ice had covered continents, sealed oceans, and reflected the sun's warmth back into space. The climate system had collapsed. And yet, something in the heart of the planet had resisted. The rocks told that story too. They carried not just the evidence of death, but the memory of survival. The Snowball Earth theory didn't begin with a grand idea. It began with the patient work of scientists who read the past through stone and sediment. They didn't expect to find a frozen planet, but once they saw the signs, they couldn't look away. And the more they dug, the more the past revealed itself. Not just as a history of ice, but as a warning of what Earth is capable of. To understand how extreme the Snowball Earth episodes were, we must first know when they occurred. This wasn't a single brief catastrophe, like a sudden storm or a flash freeze. It was a set of long, drawn-out events, each lasting millions of years. These were not just geological chapters, they were entire volumes of time, when Earth hovered between survival and extinction. And all of them took place during one of the most mysterious periods in Earth's history, the Neoproterozoic era. This era began roughly 1 billion years ago and ended around 541 million years ago. During this time, life was still limited to simple organisms. The air was changing, the continents were shifting, and strange things were happening in the oceans. But in the middle of it all, between 720 and 635 million years ago, something drastic occurred. The world plunged into at least two massive and global glaciations. These are now known as the Sturtian and the Marinoan glaciations. The Sturtian glaciation began around 717 million years ago and may have lasted over 50 million years. This was the first and perhaps most severe of the snowball events. Glaciers reached the equator. The planet's surface temperature dropped so low that ice covered almost every inch of land and sea. Entire ocean currents shut down. Life, if it survived at all, did so in isolated pockets hidden from the worst of the cold. After the Sturtian ended, the planet may have enjoyed a brief interlude, a warming period where the ice melted, carbon dioxide levels dropped again, and some form of stability returned. But this peace did not last. Around 650 million years ago, a second great freeze began. This was the Marinoan glaciation. It was slightly shorter, perhaps lasting 15 million years, but it was still catastrophic. The ice returned, the oceans froze once more, and Earth entered a second snowball phase. There may have even been a third event, known as the Glaciers glaciation, around 580 million years ago. It wasn't quite as widespread, and some scientists debate whether it reached full snowball conditions. But it still left behind glacial deposits in strange places and hints of a world still recovering from its deep freeze. What's important to understand is that these glaciations didn't just happen randomly, they were spaced out over time, with long, warm periods in between. But each one left a lasting mark on the planet. Each one changed the oceans, the atmosphere, and the path of life itself. When we think about time, millions of years can feel abstract. But imagine this: humanity, from its earliest ancestors to the present day, has existed for about 2 million years. The snowball glaciations lasted longer than the entire timeline of human history, each one a slow-motion catastrophe, freezing the world layer by layer, while life waited and endured. Scientists pinpointed the timing of these events using advanced dating techniques. They examined tiny crystals called zircons, which contain uranium. Over time, uranium decays into lead at a steady rate. By measuring the ratio of uranium to lead, researchers can calculate the exact age of the rock in which the crystal formed. It's like reading the clock of deep time, hidden inside a grain of stone. Other methods include studying magnetic signatures in rocks. When molten rock cools, minerals inside it align with Earth's magnetic field. By analyzing these alignments, scientists can figure out the ancient positions of continents. They discovered that many of the glacial deposits from these periods formed at low latitudes near the equator, and that sealed the truth. The ice had not just touched the tropics, it had conquered them. The time frame of Snowball Earth tells us that these were not isolated weather events. They were global climate shifts that lasted for tens of millions of years. They reshaped the geology of the planet. They pressed pause on biological progress. And when they finally ended, they left behind a world forever changed. The snowball episodes were not the end of life, but they came close, and without them, the planet we know today, full of forests, animals, and human civilization, might never have existed. Because sometimes, it takes the harshest conditions to push life toward new beginnings. The numbers cannot capture the feeling. The cold that gripped Earth during the snowball episodes was not the kind that stings the skin or numbs the fingers. It was the kind that crushed entire ecosystems, sealed the oceans, and silenced the sky. It was cold so deep, so absolute, that it stopped the natural rhythms of the planet. Temperatures plummeted far beyond anything humans have ever experienced, and they stayed there for millions of years. Scientists estimate that during the peak of the snowball glaciations, global average temperatures may have dropped below -50 degrees Celsius. At the equator, where modern temperatures can reach 30 or 40 degrees, it may have hovered just below freezing. And while that might seem mild on paper, it was enough for thick sheets of ice to form even in the warmest parts of the world. These were not patches of frost or seasonal snow. They were glaciers, permanent, towering, and relentless. On the continents, ice sheets may have been kilometers thick, grinding down mountains and dragging stones across the land. On the oceans, the ice stretched endlessly. It may have reached up to a full kilometer in thickness, covering the seas with a solid barrier that blocked sunlight, gas exchange, and movement. The surface of the planet became reflective, bouncing sunlight back into space, reinforcing the cold, and locking Earth in a feedback loop of deep freeze. Beneath that ice, the oceans may have remained liquid in some regions, kept warm by geothermal heat from the planet's interior, but this water was trapped. No wind stirred it. No currents circulated it. It became stagnant and dark, with little oxygen. For the tiny life forms living below, survival was not about thriving. It was about hiding, enduring, and waiting. The atmosphere itself changed. With ice covering nearly every surface, the chemical interactions between air and land were disrupted. Greenhouse gases like carbon dioxide, which normally would be absorbed by rocks and trees, began to build up. The cold air held less moisture, leading to global dryness. Snowstorms became rare. There was almost no precipitation at all, just a steady, lifeless chill that blanketed the planet. From space, Earth would have looked like a pale white marble, a world without oceans, a planet without color, its clouds muted, its surface frozen. The blues and greens of today's Earth replaced by a harsh, icy silence. And unlike a modern winter, there was no spring to follow. This cold endured, season after season, generation after generation of microbial life endured the same frozen stillness. The ice did not retreat. It remained locked in place, sealing the planet in a deep, unbroken slumber. For humans, even short exposure to such conditions would be fatal. Frostbite would set in within minutes. Breathing would become difficult. Crops would die. Oceans would stop supporting life. And yet, on Snowball Earth, this was not a survival test for a few years. It was the new reality. It became the background against which evolution had to navigate. What made this cold even more terrifying was not just its strength, but its stability. In most ice ages, fluctuations in Earth's orbit, solar output, or volcanic activity can warm the planet again. But on Snowball Earth, the feedback loop was too powerful. Ice reflected sunlight. Sunlight failed to warm the surface. More ice formed, and the loop continued. Once the snowball state was achieved, there was no natural escape, not without something drastic. This is the part that haunts scientists. The idea that Earth, once frozen in this way, might never have recovered if not for the slow and steady buildup of greenhouse gases. Without volcanic eruptions pumping carbon dioxide into the sky over millions of years, the planet may have remained a snowball forever. The ice might never have melted. Life might never have grown beyond bacteria. And Earth might have become just another dead world in a silent solar system. The cold of Snowball Earth was more than a temperature. It was a force, a weight pressing down on life, on ecosystems, on the planet's ability to breathe. It reshaped continents. It altered the oceans. And it pushed every living thing to the edge of extinction. Earth is not fragile, but it is finely balanced. The Snowball Earth events were not the result of a single catastrophe. They were the product of slow changes building over time, tipping the planet from stability into chaos. Understanding what caused such a massive freeze means looking deep into Earth's climate system, its atmosphere, its geology, and the invisible forces that link them all together. One of the key suspects is a planet-wide drop in greenhouse gases, especially carbon dioxide. Today, we think of carbon dioxide as a threat, warming the planet and altering the climate. But in the ancient world, it was one of the few things standing between Earth and deep freeze. Without enough carbon dioxide in the atmosphere, heat from the sun escapes back into space and the planet begins to cool. This is exactly what scientists believe may have happened before the snowball events began. Over millions of years, continents had begun to drift and collide. Massive new mountain ranges rose from the sea. With these mountains came increased weathering, a process where rainwater, rich in carbon dioxide, reacts with rocks and pulls the gas out of the atmosphere. As more rock was exposed, more carbon dioxide was drawn down. Slowly, the levels in the air dropped, and with less carbon dioxide to trap heat, the planet began to cool. Some theories suggest that the trigger may have come from the equator itself, a supercontinent, possibly Pangaea in one of its earlier forms, may have been positioned near the tropics. This exposed vast areas of land to intense sunlight and heavy rains. Both conditions increased the rate of chemical weathering, sucking carbon dioxide out of the sky even faster. As the atmosphere cooled, glaciers began to form at the poles. At first, this seemed like a normal ice age, but then the feedback loop began. As more ice formed, more sunlight was reflected back into space. Less energy reached the surface. The planet cooled further. The ice spread. Each new layer of white strengthened the effect, until the point came when the ice reached the oceans, then the equator, and then everywhere. Another possible factor was the sun itself. During the Neoproterozoic era, the sun was slightly dimmer than it is today. By even a few percent, this reduction in solar energy may have left the planet more vulnerable to cooling. In a world with lower greenhouse gases and a weaker sun, the margin for error became razor thin. Just a small shift could trigger runaway ice growth. Volcanic activity may have also played a dual role. While volcanoes release carbon dioxide, they can also eject aerosols and ash that reflect sunlight. If there were periods of intense eruptions that filled the sky with reflective particles, they could have temporarily blocked solar heat, cooling the atmosphere. And if that happened during an already unstable period, it might have been enough to push the planet into a snowball state. Some researchers also looked to biology. Around the time of the first snowball event, photosynthetic organisms, simple algae and bacteria had spread across the oceans. These organisms absorbed carbon dioxide to fuel their growth. In doing so, they may have reduced atmospheric carbon dioxide further, weakening the greenhouse effect and accelerating cooling. Life itself, ironically, may have helped trigger the crisis that nearly destroyed it. But no matter which combination of factors started the freeze, the result was the same. The climate tipped, the cooling became unstoppable, and once the ice began to dominate, Earth lost its ability to correct the balance. This shows just how interconnected the planet's systems are. Atmosphere, geology, biology, and sunlight all form part of a complex network. When that network is disrupted, even slightly, the results can be extreme. Snowball Earth was not just a lesson in cold. It was a warning about the planet's sensitivity to change. Earth has always walked a narrow path between too hot and too cold. During the Neoproterozoic, that balance was shattered, and what followed was a world locked in ice, with no easy way back. Sometimes, the most dangerous forces are the quietest ones. Not a storm, not a fire, but a mirror. Earth, like every planet, reflects some of the sunlight it receives. This reflectivity is known as albedo, and during the Snowball Earth events, it became a silent weapon, one that turned a cooling trend into a runaway freeze, one that nearly erased life from the surface of the world. Albedo is simple in concept. Bright surfaces reflect sunlight. Dark surfaces absorb it. Ice and snow reflect up to 90% of the solar radiation that hits them. In contrast, oceans and forests absorb most of that energy, converting it into heat. This balance of reflection and absorption is part of what keeps Earth's climate stable. But what happens when that balance is broken? Before the snowball episodes began, Earth had already started to cool. Carbon dioxide levels had dropped. Perhaps the sun had dimmed slightly. Glaciers began to form in the polar regions. And with those early glaciers came a rise in planetary albedo. As ice spread, more sunlight was reflected back into space. Less energy reached the surface. Temperatures dropped further. More ice formed. And the cycle repeated. This was the feedback loop, a trap hidden within Earth's climate system. The more the planet cooled, the more reflective it became. And the more reflective it became, the faster it cooled. A self-reinforcing spiral with no natural break. Scientists believe that once ice reached a critical latitude somewhere around 30 degrees from the equator, it triggered full planetary glaciation. The oceans froze. The continents vanished beneath white. The clouds thinned, offering no warmth. The planet became a giant mirror, bouncing sunlight away into the void. And unlike other natural cycles, this one was nearly impossible to reverse, because once the ice was in place, it kept the planet cold. Even if greenhouse gases began to rise again, the overwhelming albedo of the frozen surface could resist warming for thousands or even millions of years. Only an enormous buildup of atmospheric heat could break through. This feedback loop explains why Snowball Earth was not just an ice age, but something far more extreme. Normal ice ages come and go, with changes in Earth's orbit or solar output. But Snowball Earth locked the planet into a new state, one where even the tropical oceans were covered in ice. one where every hour of sunlight was reflected back into space without warming the ground below. The oceans, sealed beneath a solid sheet of ice, lost their connection to the atmosphere. Winds slowed, ocean currents stopped, gas exchange ceased, heat was no longer circulated. Life beneath the surface became trapped in isolated pockets, separated by layers of ice and darkness. The Earth became not just cold, but quiet. Even if volcanoes continued to erupt beneath the ice, their warmth was not enough to break the surface. And even if life continued to release carbon dioxide, there was nowhere for that heat to go. The albedo held it out, the feedback loop ignored it, and the silence endured. This runaway effect is one of the reasons why Snowball Earth is still studied with such intensity. It shows that climate systems can change not gradually, but explosively. That once certain thresholds are crossed, the planet doesn't slow down, it accelerates. And by the time signs become visible, it may already be too late. The albedo feedback was nature's trapdoor, a hidden mechanism waiting for the right conditions to activate. And when it did, it sealed Earth in ice from pole to pole. It was not the biggest force, but it was the most efficient, and it held the planet in its grip for millions of years. Beneath the frozen crust of Snowball Earth, the planet's heart was still beating. While the surface was locked in silence, the deep interior remained alive. Volcanoes, fueled by the restless movements of tectonic plates, did not sleep. They erupted in darkness, beneath thick glaciers and frozen seas. And in the end, it was these volcanoes that would change everything. For millions of years during the Snowball episodes, the planet remained encased in ice, but underneath, the forces of geology continued without pause. Magma pushed its way through cracks in the crust. Pressure built in chambers deep underground, and eventually, molten rock, ash, and gases forced their way out into the world above, even if that world was buried in ice. Some of these eruptions happened beneath the oceans, under kilometers of frozen sea. Others occurred on land, where the weight of the glaciers added even more pressure to the molten chambers below. When a volcano erupted beneath the ice, the heat from the lava melted tunnels and chambers, creating sudden lakes and rivers that boiled and steamed within the frozen shell. But these were temporary. The heat never lasted long enough to melt the full thickness of the glaciers. The ice always closed back over the wound. Still, these eruptions did more than just bring heat. They brought gases, and the most important of those was carbon dioxide. Volcanoes are one of Earth's most powerful sources of carbon dioxide. And during Snowball Earth, with weathering processes nearly stopped due to the ice cover, this gas began to build in the atmosphere with no place to go. Normally, carbon dioxide released by volcanoes is pulled from the sky by rainfall and chemical reactions with exposed rock, but Snowball Earth had sealed those systems. There were no trees, no rain, and no rock faces to absorb the gas, so it accumulated. Year after year, century after century, the sky began to thicken with an invisible blanket. Over millions of years, the concentration of carbon dioxide grew to levels far higher than anything seen before or since. Some estimates suggest it may have reached over 1,000 times today's levels. And with every additional molecule, the greenhouse effect strengthened. This was the beginning of the end for Snowball Earth. Not a sudden melt, but a slow pressure building in the atmosphere. Eventually, the blanket of greenhouse gases became thick enough to trap significant heat. Sunlight, once reflected by the ice, began to have an effect. Tiny melting points formed across the frozen world, and once the ice started to crack, the albedo feedback loop reversed. Melting exposed darker surfaces beneath. Oceans, rock, and soil began to absorb sunlight instead of reflecting it. This led to more warming, more melting, and a chain reaction. The frozen shell shattered, not all at once, but piece by piece. Glaciers retreated, oceans opened, rain returned, and for the first time in tens of millions of years, Earth breathed again. The volcanoes had never stopped, but only their patience, their slow and steady emissions, had the power to outlast the grip of the ice. They did not bring immediate rescue. They brought the conditions for recovery. And when those conditions were finally met, the planet awoke from its slumber. Yet the end of the freeze was not gentle. With so much carbon dioxide in the sky, the warming was extreme. Temperatures soared. The oceans boiled with released gases. Floods swept across the continents. The ice melted rapidly, unleashing fresh water into the salty seas, disrupting currents and chemistry. The Earth went from snowball to hothouse in what may have been one of the most dramatic climate transitions in history. All because volcanoes kept breathing beneath the silence. They were the planet's lifeline, its underground lungs, its hidden fire. And in the darkest, coldest era of Earth's story, they held the key to survival. Before the world was locked in ice, before the oceans were sealed beneath glaciers and sunlight faded from the surface, life had already taken root on Earth. It was not complex. There were no animals, no plants, no forests, and no bones, but life existed, quietly, patiently, and it had already begun to shape the planet in ways that would later decide its fate. Life before the Snowball Earth events was mostly microbial. Single-celled organisms dominated the oceans, drifting in sunlit waters and clustering around nutrients. These tiny life forms, bacteria, archaea, and early eukaryotes, had spent billions of years evolving from the first spark of life in Earth's ancient seas. They had survived mass extinctions, meteor impacts, and toxic atmospheres, and by the time of the Neo-Proterozoic era, some of them had developed a powerful trick: photosynthesis. Photosynthesis was revolutionary. It allowed organisms to convert sunlight into energy, and in doing so, release oxygen into the environment. Over hundreds of millions of years, these photosynthetic microbes transformed the atmosphere, slowly increasing the oxygen level and making the planet more hospitable to future life. They floated in vast mats called microbial stromatolites and cyanobacterial colonies, soaking up sunlight and shaping the chemistry of the oceans. This oxygenation event, sometimes called the Great Oxygenation, had begun long before Snowball Earth. But by the Neo-Proterozoic, the rise in oxygen was starting to have more visible effects. It allowed for more complex cells to evolve. Eukaryotic cells, which contain nuclei and internal structures, began to appear. These were the ancestors of all complex life, including animals, plants, and fungi. In some areas, primitive multicellular life was beginning to emerge. Small, soft-bodied organisms. Strange jelly-like creatures with no hard parts. The first steps toward the diversity of life we know today. But this evolutionary progress was fragile. The biosphere was still young, still experimenting, still finding its balance. And most of these life forms depended on the ocean's surface for light, warmth, and nutrients. The ecosystems that had formed were shallow and delicate. They lived where the sun could reach, where currents stirred food through the water, and where gas exchange between the ocean and the atmosphere allowed oxygen to dissolve into the sea. There were also microbial communities, living in extreme environments around hydrothermal vents in the deep ocean. Where sunlight never reached, chemosynthetic organisms thrived. These life forms used chemicals instead of light to survive. They had evolved independently from the surface ecosystems, and although small in number, they were resilient, adapted to high pressure, heat, and isolation. Still, the vast majority of life before Snowball Earth depended on access to light. Photosynthetic organisms needed open water, and complex cells needed oxygen. When the freeze began, these needs would become vulnerabilities. Before the first snowball event, The Sturtian glaciation life had already begun to form microbial mats across the seafloor. Algae had spread through the shallow coastal waters. Plankton had begun to dominate the sunlit upper ocean. All of this was erased or buried when the glaciers came. The ice sealed the oceans, blocked the sun, and cut off the flow of gases. Photosynthesis nearly stopped. Oxygen levels dropped, and complex life faced extinction. The fossil record from this period is sparse, not because life was absent, but because most organisms had no hard parts to preserve. What remains are impressions in ancient sediments, chemical traces of biological activity, and microscopic fossils of cells. These fragments tell us that life was preparing to take a major leap forward. Snowball Earth interrupted that leap. It was a pause in the experiment of evolution, a test of endurance before the explosion of diversity that would follow millions of years later. Life before the freeze was small, simple, and fragile, but it was also persistent. It had already weathered billions of years of chaos. And even as the glaciers formed and the world began to darken, some of that life would find ways to survive. As the ice closed over the oceans and the skies dimmed, life on Earth entered its darkest trial. The surface became silent. The continents were buried in white. The seas, once full of drifting microscopic life, lay beneath a lid of solid ice. For millions of years, sunlight barely touched the planet's surface. Temperatures dropped. Oxygen levels fell. Yet somehow, in this frozen stillness, life did not vanish. Survival during Snowball Earth was not about growth or expansion. It was about hiding, adapting, holding on with the barest grip. The planet had become hostile to nearly every known form of life. Photosynthetic organisms could no longer access sunlight. Ocean circulation had slowed or stopped. Nutrients were trapped beneath the ice. And yet, a few tiny outposts of resilience remained. The most likely refuges were found in the deep sea, around hydrothermal vents. Here, superheated water rich in minerals poured from the Earth's crust, creating a pocket of warmth and chemical energy in an otherwise frozen world. Around these vents, chemosynthetic bacteria and archaea continued to thrive. They did not need sunlight. They used hydrogen sulfide and other compounds from the vent water to power their survival. This life was primitive but robust. It had evolved long before the snowball and could endure in the absence of light. These vent communities may have been the last strongholds of life during the deepest freeze. Shielded by kilometers of water and ice, they operated in complete darkness, in silence, immune to the surface chaos. Their existence proves that not all life depends on the sky. But the deep sea was not the only possible sanctuary. Some scientists believe that thin patches of equatorial sea ice allowed small regions of open or partially frozen water. These patches may have formed where the ice was thinner due to sunlight hitting more directly, or where geothermal heat from the ocean floor kept small holes open. In these pockets, photosynthesis may have continued. Barely. Microbial mats could have lived just beneath the surface, using what little light managed to filter through. Even within the ice itself, life may have found shelter. Cryoconite holes, small melt depressions filled with dust, microbes, and liquid water, can form on glacier surfaces today. If similar structures existed during Snowball Earth, they could have supported microbial life, insulated by ice, and nourished by occasional sunlight and nutrients trapped in dust particles. These icy microhabitats would have been tiny islands of life in a world of cold. Beneath glaciers on land, subglacial lakes might have remained unfrozen. Pressure from the thick ice above, combined with geothermal heat from below, can keep water liquid even under extreme cold. Microbial life in these lakes could have persisted, isolated for millions of years, evolving slowly in the dark. In the ocean depths, anaerobic microbes, organisms that live without oxygen, could have continued breaking down organic matter. These life forms do not require light or oxygen and can survive in extreme environments. Their presence would have added one more layer to the survival web during this time. However, most surface-dwelling photosynthetic life likely perished. The long freeze starved these organisms of light, warmth, and nutrients. Their extinction caused a collapse of food chains. The oceans became a biological desert, with only the hardiest microbes able to endure. The lack of oxygen during the snowball events was another deadly challenge. As photosynthesis slowed or stopped, oxygen production dropped. The oceans became anoxic, filled with dissolved iron and devoid of breathable gases. This shift caused a temporary return to the chemical conditions of early Earth, before oxygen had begun to dominate. For millions of years, evolution slowed. The complex cells that had begun to emerge before the freeze were pushed back, their progress halted, but not erased. Deep below the ice, in vents, cracks, and briny films of meltwater, life waited. It endured in silence, storing the memory of survival in its DNA. Snowball Earth did not destroy life. It filtered it. Only the most adaptable survived, and from those survivors, the next great leap in evolution would one day arise. But during the long frozen centuries, the world belonged to the smallest, simplest creatures, quiet, unseen, and unbroken. In a world where the surface was silent and the oceans sealed shut, survival required more than strength. It required creativity, flexibility, and most of all, patience. The organisms that endured Snowball Earth were not the largest or the fastest. They were the ones that could slow down, hold on, and adapt to the harshest conditions the planet had ever seen. The first and most important strategy was isolation. Life retreated into places where the cold could not reach as deeply. Hydrothermal vents on the ocean floor were among the safest havens. Here, superheated fluids erupted from cracks in the seafloor, creating a stable source of heat and energy in an otherwise frozen planet. Microbes clustered around these vents, using chemosynthesis to fuel their survival. Instead of sunlight, they relied on chemicals like hydrogen sulfide and methane. This was life on Earth's terms: silent, extreme, and self-sufficient. Another key strategy was entering a dormant state. Many microorganisms are capable of slowing their metabolism to a near-complete halt. In this state, they can survive without food, without warmth, and without light. Some may have formed protective spores, hard shells that could resist freezing temperatures, high pressure, and radiation. These dormant cells drifted through the dark oceans or sat buried beneath sediments, waiting for the world to change. In the thin areas of equatorial ice, some light still filtered through. In these rare and fragile zones, microbial mats may have continued photosynthesis during brief windows of sunlight. Some of these organisms were likely psychrophiles, cold-loving microbes that actually thrive at low temperatures. Modern psychrophiles live in Antarctic sea ice and deep glacial lakes. During Snowball Earth, their ancestors may have been the last active producers of oxygen and nutrients. Life also adapted by forming communities. Microbial colonies could survive better together than alone. By sticking to one another and creating biofilms, slimy, protective layers, they trapped moisture, shared resources, and created localized microenvironments more stable than the world around them. Some of these biofilms formed inside ice, inside rock pores, or beneath thin layers of sediment where geothermal heat still reached. In subglacial lakes and meltwater pockets beneath the ice, another survival strategy emerged: chemical recycling. These hidden lakes were cut off from the surface for millions of years. But microbial life inside them developed closed-loop systems, where waste products from one species became food for another. In total darkness, without any connection to the atmosphere, these communities built self-contained ecosystems, proving that life needs neither light nor open air to survive. The limited movement of ocean water also led to strange adaptations. Some organisms evolved to function with minimal oxygen. Others relied on fermentation or chemical reactions that didn't need oxygen at all. In these anoxic zones, the ancient chemistry of life returned processes that had dominated billions of years before oxygen became common. It was a reawakening of Earth's oldest survival tools. Even the shape of life may have changed. Smaller organisms have an easier time surviving extreme environments. They require fewer resources, they can reproduce quickly, and they can hide in places larger organisms cannot. During Snowball Earth, tiny size became an advantage, and those who could replicate their DNA in freezing conditions would pass on traits that would later fuel the explosion of life when the planet thawed. Survival wasn't just physical, it was chemical, environmental, and evolutionary. Every adaptation was a response to pressure, and the pressure was relentless. No sunlight, no fresh oxygen, no circulation of nutrients, no changing seasons, only cold, darkness, and silence. But the blueprint for endurance was already written in the simplest forms of life: flexibility, cooperation, the ability to wait. Life didn't conquer Snowball Earth by fighting it. It survived by slipping into its cracks, hiding in its warmth, and outlasting its fury. These survival strategies laid the foundation for everything that followed, because when the ice finally melted and the oceans opened again, it was the descendants of these hidden survivors that would reclaim the planet, and in time, evolve into forms far more complex, beautiful, and powerful than the Earth had ever seen. On the surface of glaciers and ice sheets, where the cold is absolute and life seems impossible, there exist small, dark specks. From a distance, they look like imperfections in the ice, meaningless patches of dust. But up close, they tell a different story. These are cryoconite holes, tiny, meltwater depressions filled with dark sediment and living microbes. And during Snowball Earth, they may have been among the last sunlit refuges for life. A cryoconite hole forms when dark particles, like dust, ash, or microscopic debris, land on the surface of ice. These particles absorb more sunlight than the surrounding white ice, causing the area beneath them to melt slightly. Over time, the depression deepens, filling with meltwater. Inside, a microhabitat emerges. Light filters through the ice. Water remains liquid, trapped in the depression, and in this temporary pool, life can exist. Modern cryoconite holes, found in Greenland and Antarctica, support diverse microbial communities. Bacteria, algae, fungi, and even microscopic animals live within them, feeding on organic matter, exchanging gases, and reproducing in the narrow band of liquid surrounded by ice. They are ecosystems on a miniature scale, isolated, resilient, and surprisingly complex. During the Snowball Earth events, when most of the ocean was frozen and surface life had collapsed, cryoconite holes may have provided one of the few habitats where photosynthesis could continue. In regions near the equator, where the sun still shone weakly and the ice may have been thinner, cryoconite holes could form more easily. And once formed, they offered a small but crucial advantage: access to light and liquid water. Photosynthetic microbes, like cyanobacteria, could thrive in these depressions, using filtered sunlight to generate energy and produce oxygen. The water, though cold, remained above freezing. The dark particles also brought minerals and nutrients. Over time, a self-contained ecosystem could form, fed by the sun and protected by the ice. These cryoconite ecosystems would not have been widespread. They were rare, fragile, and constantly threatened by refreezing, shifting ice, or burial under snowfall. But even a small number of them could have made a difference. They acted as stepping stones for life, allowing key organisms to persist through the worst phases of glaciation. Inside a cryoconite hole, life was limited to millimeters of water. Temperatures were near freezing. Oxygen levels were low. Nutrients were scarce. And yet, these challenges mirrored conditions in many of Earth's extreme environments today. And just as modern microbes have adapted to Antarctic ice, their ancient ancestors may have done the same. The structure of the hole also created protection. The ice above filtered harmful radiation, shielding the microbes from ultraviolet light. The meltwater remained stable due to the insulating properties of the ice walls, and the sediment at the bottom acted as a reservoir for minerals and food. If Snowball Earth's ice sheets were anything like today's, they may have supported millions of these microhabitats across the planet's equatorial belt, scattered and shallow, but collectively significant. Not enough to restore the planet's ecosystems, but enough to keep key life forms alive. These cryoconite holes, humble and overlooked, may have preserved the very organisms that would later seed the oceans when the ice melted. They are proof that even in the most hostile conditions, life can carve out a place for itself not through dominance, but through adaptation. In the story of Snowball Earth, cryoconite holes were not grand refuges. They were flickering embers, small, isolated sparks of life waiting beneath a ceiling of ice. And when the thaw finally came, those sparks would help reignite the world. As Earth froze and the oceans disappeared beneath kilometers of solid ice, the question that lingered in the shadows was simple yet terrifying. Did photosynthesis stop? And if it did, how did life continue? The answer is not absolute, but it reveals just how close the planet came to biological silence. Photosynthesis is the foundation of nearly all complex life. It converts sunlight into energy and, in doing so, produces oxygen. Without it, the oceans become starved of breathable gases and food chains collapse. Before Snowball Earth, photosynthetic organisms like cyanobacteria and algae dominated the sunlit upper layers of the sea. Their energy production fed entire ecosystems, and their oxygen output slowly shaped the atmosphere itself. They were invisible power plants floating in water, transforming the planet. But when the freeze began, the first blow was to the sun. The growing ice reflected more and more sunlight back into space. The equator, once bathed in tropical warmth, turned white. The oceans began to seal over, first with seasonal ice, then permanent glaciers. As the layers thickened, light could no longer penetrate. The surface darkened, and photosynthesis faltered. In most parts of the planet, it likely stopped entirely. Under thick continental glaciers and frozen seas, no light reached the microbial mats and algae that once covered shallow seabeds. The energy source was gone, and so, for millions of years, photosynthetic life retreated or vanished. But not everywhere. Scientists believe that in certain regions, particularly near the equator, thin patches of sea ice may have allowed some light to filter through. These areas, fragile and scattered, were likely maintained by geothermal heat from the ocean floor or by the sun's more direct angle at lower latitudes. Beneath these translucent layers, a faint glow persisted, and in that glow, some photosynthetic microbes may have continued their work. Modern analogues can be found in Antarctica, where algae and bacteria survive beneath sea ice that is only a few meters thick. These organisms use the dim light to fuel photosynthesis, even during the long polar night. Their ancient ancestors may have done the same during Snowball Earth, clinging to any available photon, adapting to extreme cold, and evolving light-harvesting systems that worked in near darkness. In cryoconite holes, those sun-warmed melt pockets on the surface of the glacier's photosynthetic life may have also continued. Though isolated and tiny, these pools offered liquid water, nutrients, and light. In them, cyanobacteria and other microbes could grow slowly, sustaining themselves and producing small amounts of oxygen. In addition, some researchers suggest that cracks in the sea ice, leads, or polynyas openings formed by wind or ocean currents might have created temporary windows for light to reach the water. In these narrow corridors, short-lived photosynthetic blooms could have occurred, providing bursts of energy and nutrients that helped sustain microbial communities below. Still, compared to the thriving biosphere that existed before the glaciation, the level of photosynthesis during Snowball Earth was drastically reduced. The global oxygen supply would have dropped. Organic matter production slowed to a crawl, and food webs collapsed to their simplest forms. It was survival in slow motion, a biological winter that lasted for tens of millions of years. Yet even this dim, struggling form of photosynthesis may have been enough. It kept certain key organisms alive. It maintained a minimum level of oxygen in the oceans, and it preserved the possibility of recovery once the ice retreated. Photosynthesis did not thrive during Snowball Earth, but it didn't disappear either. Instead, it hid, in the cracks, in the thinnest ice, in the warmest corners of a frozen world. And when the sun returned, it was waiting, ready to bloom again and remake the planet. Measuring time in Earth's deep history is like counting shadows in a cave. There are no clocks, no records, only layers of rock, isotopes in crystals, and chemical signals locked in stone. Yet even through these silent records, scientists have pieced together the chilling truth: Snowball Earth wasn't a brief episode. It wasn't a single season of catastrophe. It was an era, a frozen chapter that lasted for tens of millions of years. The most extreme of these glaciations, the Sturtian and the Marinoan, are estimated to have lasted roughly 50 and 15 million years, respectively. Together, they represent one of the coldest and most prolonged climate states Earth has ever endured. 50 million years of stillness, of silence, of life hiding beneath ice. The sheer scale of that time frame defies imagination. To understand just how long that is, consider this: modern humans have existed for only about 2 million years. All of recorded history fits into just the last 10,000. Yet the Sturtian glaciation alone lasted 25 times longer than the entire span of human civilization. During that time, continents shifted, mountains eroded, volcanoes rose and fell, and life, if it survived at all, did so in near total isolation. The length of the freeze was not constant everywhere. Some regions may have experienced shorter glacial pulses within the larger snowball period. Others may have been locked in ice for the entire duration. But overall, the planet remained cold, reflective, and biologically suppressed for a geological eternity. Scientists determined the duration of these glaciations through radiometric dating. They use elements like uranium and lead, locked in tiny zircon crystals, to calculate the age of volcanic ash layers found above and below glacial deposits. These methods are precise, sometimes down to a few 100,000 years, and they consistently show that the glaciations were not short-lived. Additional clues come from the rock layers themselves. Thick sequences of glacial tillites, sedimentary rocks formed by ice, suggest that glaciers advanced and retreated many times. Chemical signals in carbon isotopes show major disruptions in the carbon cycle lasting for millions of years. These disruptions are consistent with a planet sealed in ice, where biological productivity dropped and organic carbon burial slowed to a crawl. Fossil evidence supports this timeline too. Before the snowball events, microbial fossils are common in many parts of the world. During the glaciations, they become rare or vanish altogether. And after the ice melts, new forms of life begin to appear, as if the planet had hit reset. This biological pause aligns with the geological record of a world trapped in cold stasis. The long duration of the freeze posed one of the greatest threats to life. Short disasters like volcanic eruptions or asteroid impacts can be devastating, but they pass. Snowball Earth did not pass quickly. Its pressure was constant, its grip unbroken. And for life to survive, it had to evolve not just resistance, but patience. Some scientists suggest that there may have been short-lived warm intervals within the snowball period, brief episodes where volcanoes erupted in clusters, releasing bursts of greenhouse gases, or where orbital changes tilted the planet just enough to melt parts of the equator. These warm pulses might have allowed limited recovery of photosynthesis and biodiversity, only to be followed by renewed glaciation. If so, the snowball period was not a single freeze, but a cycle of near-complete planetary collapse and fragile rebound. What's remarkable is that even after tens of millions of years of ice, Earth came back. Not only did the ice eventually melt, but life rebounded with astonishing power. The thawing world became fertile ground for evolution. And in the wake of the snowball events, new forms of complex, multicellular organisms began to appear. This resurgence laid the groundwork for the explosion of life that would later transform the oceans and eventually give rise to animals. But during the snowball itself, time seemed to stop. The sun rose and set over a lifeless surface. Glaciers scraped the land in slow silence. Beneath the ice, tiny pockets of life counted each generation in microscopic steps, waiting for the moment when the world would shift and the light would return. For tens of millions of years, Earth remained locked in a state of silence. Glaciers blanketed the continents. The oceans lay sealed beneath ice. The sun shone, but its light could not warm the surface. No storms, no rivers, no seasons, only stillness. And yet, beneath that frozen shell, change was building, not sudden, not loud, but constant and unstoppable. The end of Snowball Earth did not come from above, it came from below. While the surface froze, volcanoes deep beneath the crust continued to erupt. Magma rose from the mantle, feeding underwater ridges and island arcs. Each eruption released carbon dioxide into the atmosphere. Normally, this gas would be balanced by natural processes like chemical weathering, where rain dissolves carbon dioxide and locks it away in rock. But during the snowball state, that balance was broken. The land was buried under ice. The rain had stopped, rivers had dried, and weathering had all but ceased. So the carbon dioxide had nowhere to go. It remained in the atmosphere, accumulating year after year, century after century, slow at first, invisible, but steady. The planet became a giant pressure cooker, its heat trapped by a growing blanket of greenhouse gas. As carbon dioxide levels rose, the greenhouse effect began to intensify. The sunlight that once bounced harmlessly off the icy surface now started to linger. The thin air began to warm. And somewhere, over some forgotten sea, the ice began to crack. Melting did not happen everywhere at once. It began at the edges, at high points, in places where the ice was thinnest or the sunlight strongest. Each new patch of exposed ground absorbed more heat, accelerating the process. The albedo effect, once the cause of the deep freeze, now worked in reverse. As ice disappeared, more energy was absorbed. More heat was retained. The feedback loop that had once frozen the planet now drove its awakening. As the surface warmed, meltwater began to flow. Glacial lakes formed and spilled. Torrents of water carved channels through the ice. Vast floods roared across the continents, sweeping away ancient sediment and rock. Entire landscapes were reshaped in a matter of weeks. The oceans, too, responded. As the surface ice melted, sunlight returned to the upper layers. Photosynthetic microbes awakened. Oxygen levels began to rise. Nutrients locked in the glaciers were released. fueling sudden blooms of life. The chemistry of the water changed, almost overnight. Banded iron formations reappeared, marking the moment oxygen and iron collided in the sea. The carbon dioxide buildup may have reached levels more than 1,000 times higher than today's. Temperatures soared. Some estimates suggest that global average temperatures shot up by dozens of degrees within a few thousand years. In geological terms, it was instant. Earth shifted from icehouse to hothouse. A planet frozen for ages was suddenly burning with tropical storms, acidic rains, and massive erosion. This transition was not gentle. As the ice melted, sea levels rose dramatically, coastlines drowned, waves of sediment flowed into the oceans. Earthquakes and volcanic eruptions surged as the weight of the glaciers lifted from the crust. It was a violent rebirth, but it was also the beginning of something new. With the return of liquid water and warmth, life re-emerged with force. The survivors of Snowball Earth, those who had clung to hydrothermal vents, cryoconite holes, and subglacial lakes, now had an open world. Oxygen began to accumulate again in the atmosphere. The climate stabilized. The oceans reconnected. Ecosystems reassembled. The end of the snowball was more than the melting of ice. It was the reawakening of the planet itself. It showed that even after the deepest freeze, Earth could return, it could heal, and it could become fertile ground for the next stage of evolution. In the silence of deep time, the thaw was not just a climatic event, it was a turning point. From that moment on, the stage was set for complexity, for movement, for vision and thought. The snow had hidden the spark of life, but it could not extinguish it. And when the ice finally cracked, the future came rushing through. Earth has always been a planet of change. It has shifted from calm seas to roaring volcanoes, from deserts to rainforests, from silence to song. But few transitions in its long history were as violent and dramatic as the one that ended Snowball Earth. In just a geological blink, the planet flipped from deep freeze to sweltering heat. It was not a gentle shift. It was a transformation marked by chaos, flooding, and fire. As the snowball thawed, the atmosphere was already heavy with carbon dioxide. For tens of millions of years, volcanoes had been pumping it into the sky without interruption. There had been no trees to absorb it, no weathering rocks to lock it away, only gas, accumulating slowly but relentlessly. By the time the ice began to melt, the greenhouse effect was already roaring at full strength. The albedo effect now worked in reverse. As the white glaciers shrank, darker surfaces like rock and ocean water absorbed sunlight instead of reflecting it. The planet's surface warmed rapidly, and with that warmth came the release of more greenhouse gases. Methane, once trapped in permafrost and undersea clathrates, escaped into the atmosphere. This potent gas added even more heat. The result was a cascade of warming that pushed the planet into unfamiliar territory. Temperatures may have risen by dozens of degrees. Sea levels surged as glaciers collapsed. The newly freed oceans swallowed ancient coastlines. Torrents of water raced over the land, eroding mountains, carving valleys, and dumping massive amounts of sediment into the sea. The weather turned wild storms, lightning, and torrential rains flooded the raw post-glacial world. The oceans, too, went through convulsions. As the surface melted, cold, oxygen-starved water mixed with warmer layers below. The chemistry of the sea shifted violently. Nutrients were released in vast quantities from the melting glaciers. These nutrients, once locked away, now triggered enormous algal blooms. Entire regions of the ocean turned green with microbial life, pulling carbon dioxide from the atmosphere and pumping oxygen back into the water. But this sudden boom had a price. The decay of these blooms consumed oxygen, sometimes leading to zones of suffocation, anoxic dead zones where nothing could survive. Life was rebounding, but it was chaotic, uncontrolled, and still fragile. Rainfall, once absent during the Snowball era, returned with a vengeance. Acid rain, formed from carbon dioxide mixing with water vapor, fell on newly exposed rock, dissolving minerals and flooding the oceans with calcium, magnesium, and bicarbonate. This, in turn, led to the formation of unusual rock layers known as cap carbonates, thin, smooth, and widespread. These carbonates were laid down rapidly across the planet, a geologic fingerprint of sudden climate reversal. Earth had entered a hothouse phase, one that may have lasted for several million years. Deserts may have formed near the equator, tropical storms battered coastlines, atmospheric circulation patterns reorganized. For organisms that had just survived a global freeze, this new world was almost as challenging as the one before. Yet this instability also meant opportunity. The intense chemical weathering of exposed rock pulled carbon dioxide from the atmosphere, slowly cooling the planet again. Oxygen levels rose, supporting more complex metabolism, and new ecological niches opened across the recovering continents and seas. The survivors of Snowball Earth now faced a world full of possibilities and full of danger. This flip from icehouse to hothouse wasn't just a temperature swing, it was a complete reset of Earth systems. Climate, chemistry, biology, and geology all collided in one of the most dramatic transitions the planet has ever seen. It was both destruction and creation. In this new, overheated world, evolution picked up speed. Life began to diversify. Cells grew more complex. Organisms learned to cooperate, specialize, and build new forms. And eventually, the foundation was laid for the rise of animals. The extremes of Snowball Earth were not simply challenges. They were catalysts. They forced life to adapt, to experiment, and to survive against impossible odds. And in doing so, they forged a planet not just capable of life, but capable of transformation. When the ice melted and the heat surged, Earth did not simply return to the way it was. It had been changed chemically, biologically, and physically. What followed was not just a recovery, it was a rebirth. A moment in deep time when life, battered and nearly extinguished, emerged again with new energy and new possibility. In the wake of the snowball, oceans were once again open to the sky. Sunlight reached the water's surface. Winds returned. Rainfall carved paths into the raw, exposed continents. The land, stripped clean by glaciers and newly scoured by floodwaters, was blank and nutrient-rich. It was a planet starting over, and into this clean slate, life returned. The first to take advantage were the microbes, bacteria, and algae, long hidden beneath ice or locked in survival mode, now bloomed in the open seas. With the return of photosynthesis, oxygen levels in the atmosphere began to rise again. The oceans filled with it. The chemistry of life, once pushed to its limits, began to stabilize. Nutrients released by glacial melt and erosion surged into the seas, fueling vast microbial blooms. The base of the food chain expanded. The oxygen produced by these blooms changed everything. Not just the water, but the very air of the planet grew more breathable, and with oxygen came new evolutionary pressures. Before Snowball Earth, life was mostly simple single cells, weak structures, little variety. But after the freeze, something shifted. With more oxygen available, cells could afford to become larger and more complex. Metabolic processes that had once been too expensive became viable. Evolution had new tools to work with, and it began to build. The fossil record starts to change. In the millions of years following the final snowball event, signs of multicellular organisms begin to appear. At first, they are soft-bodied and strange fronds, discs, and tubes preserved in rare sediment beds. These early forms are not yet animals, but they are more than microbes. They mark the beginning of the Ediacaran biota, a period when life started to experiment with shape, symmetry, and size. It's as if Snowball Earth had hit a reset button on evolution. It cleared out the weak, preserved only the most adaptable, and then opened the door to innovation. Freed from the slow stasis of the frozen world, evolution accelerated. The survivors were not just alive, they were ready to transform. On land, things remained quiet. For now, life still belonged to the oceans, but even in the water, the pace quickened. Eukaryotic cells, those with nuclei and internal structures, began to specialize. They formed colonies, then tissues, then bodies. Cooperation became a survival advantage, and with it came complexity. In some places, fossil evidence shows signs of predation organisms interacting, feeding, and responding to each other. This was new. Before, life had existed in isolation, drifting and absorbing nutrients. Now it was engaging, sensing, evolving to compete. Snowball Earth had set the stage for dynamic ecosystems. This rebirth of life didn't happen overnight. It took millions of years, but the direction was clear. The simplicity of the pre-snowball world was gone. In its place was a planet teeming with potential. The evolutionary fuse had been relit. The continents, still raw from the melting glaciers, began to shift again. Tectonic movements reassembled land masses, forming new supercontinents. Mountain ranges rose, basins filled with water. The geography of Earth became more complex, offering new habitats, challenges, and opportunities. Earth itself had survived one of its greatest trials, and in doing so, it had become something new, not just a world of microbes, but a world on the verge of animals. A world where life would no longer remain microscopic and passive, but begin to crawl, to sense, to hunt. The aftermath of Snowball Earth was not just survival, it was transformation, a rebirth that would lead, in time, to every creature that walks, swims, or flies today, including us. Long after the glaciers melted and the oceans reopened, the story of Snowball Earth remained hidden in stone. Not in bones or fossils, but in strange, smooth rock layers that drape over the older glacial deposits like a final signature. These layers are called cap carbonates, and they are among the most important pieces of evidence that Earth once froze from pole to pole and then thawed in a burst of heat and change. Cap carbonates are unique. They are thin but widespread layers of carbonate rock, mostly limestone and dolostone, that appear immediately above glacial tillites. These are the sediments left behind by glaciers. The contrast between the two layers is sharp. Beneath the cap carbonate, you find chaotic mixtures of rock scraped up by ice. Above it, you find smooth, chemically layered rock formed in calm, shallow seas. It's a geological shift, so abrupt that it suggests something sudden and global happened at the boundary. But it's not just their position that makes cap carbonates important. It's their chemistry. The carbon isotopes within them tell a story of a planet recovering from a deep freeze. Before Snowball Earth, carbon cycling was relatively stable. Photosynthesis and organic burial created a balance in the carbon isotopes found in ocean sediments. But during the glaciation, that balance was disrupted. Photosynthesis nearly stopped. Carbon was not being buried. And when the ice melted, all that trapped carbon dioxide rushed back into the atmosphere and the oceans. The result was a chemical shockwave. As the atmosphere filled with carbon dioxide, it dissolved into the warming oceans, forming carbonic acid. This reacted with the newly exposed rocks, especially silicate minerals, in a process that released calcium and magnesium into the water. Those elements, combined with carbonate ions, quickly precipitated out as limestone and dolostone, forming the cap carbonate layers we see today. These layers formed rapidly. In some places, they reach up to 10 meters thick, yet they were likely deposited over just tens of thousands of years, a geological blink. Their crystals often show signs of unusual formation conditions, like acicular, needle-like shapes that suggest high levels of saturation and rapid growth. Cap carbonates also contain strange sedimentary structures. There are ripple marks, giant crystals, and signs of microbial activity. In some locations, you even find small tubes and imprints that may have been left by primitive organisms returning to the sea floor after the ice melted. They are snapshots of a world in transition from deathly stillness to sudden rebirth. The global distribution of cap carbonates is what makes them so convincing as evidence for Snowball Earth. They appear on nearly every continent. Africa, North America, South America, Australia, Asia, all contain these post-glacial carbonate layers resting directly on top of glacial deposits. No known regional event could have produced this pattern. Only a global climate reversal can explain it. Scientists use these layers not only to prove that Snowball Earth happened, but also to time its ending. Radiometric dating of volcanic ash within or near cap carbonates helps pin down the moments when the glaciers melted. And the isotopic signatures in these rocks give insight into how fast the planet warmed and how quickly life returned. Cap carbonates are more than just rocks. They are chemical records, etched in stone, of Earth's most extreme climate event. They show that the thaw was not gradual. It was rapid, intense, and transformative. And they tell us that after the deepest freeze in planetary history, the response was not subtle, it was explosive. They also carry a warning, because they represent what happens when carbon dioxide builds unchecked in the atmosphere. The warming they record is not comfortable, it's chaotic. A climate swinging from one extreme to another. The kind of change that reshapes oceans, kills ecosystems, and rewrites the rules of survival. But most of all, cap carbonates are evidence of resilience. They mark the moment when life stepped back into the light, when the oceans calmed and chemistry realigned. They are the signature of Earth's ability to recover, to rebuild, and to begin again. After the long silence of Snowball Earth, something remarkable began to unfold. In the aftermath of global freezing, as warmth returned and the oceans stirred back to life, evolution seemed to awaken with new energy. Simple life forms that had endured the cold now began to multiply, diversify, and experiment. This period is known as the Ediacaran explosion, a time when multicellular organisms began to appear in forms more complex, more organized, and more dynamic than ever before. The Ediacaran period began around 635 million years ago, shortly after the last snowball glaciation ended. It marks the final chapter of the Precambrian era, a time still cloaked in mystery, but now illuminated by the fossils left behind in ancient seabeds. These fossils do not resemble anything alive today. They are strange, soft-bodied, and often flat, imprinted in fine sediment like forgotten shadows. Yet they represent the first large organisms ever to evolve on Earth. Before this period, life had been almost entirely microscopic. Bacteria, algae, and other single-celled organisms ruled the oceans. Even after the thaw, it took time for conditions to become stable enough for more complex life to take hold. Oxygen levels had to rise, nutrients had to circulate again, and ecosystems had to rebuild from the most basic foundations. When these conditions aligned, something shifted. The first Ediacaran organisms were simple, but large compared to anything before them. Some resembled fronds or leaves, with broad, flat bodies that lay gently on the seafloor. Others were shaped like discs, tubes, or quilts, with no clear front or back. They had no bones, no shells, no mouths, and no eyes, but they were multicellular, and they were alive in a way the planet had never seen before. They did not move quickly, if at all. Most were sessile, attached to the sea floor, absorbing nutrients directly from the water. Others may have glided slowly across the sediment, leaving behind faint tracks. They formed the first known communities of large organisms clustered together in the shallow seas, reaching toward the sunlight filtering through the water. This sudden rise of multicellular life was not a coincidence. It followed directly from the end of Snowball Earth. The melting of the glaciers released vast amounts of nutrients into the oceans. Phosphorus, iron, and other key elements fueled an explosion of primary production. Algae and microbial life bloomed, creating food sources and raising oxygen levels in the atmosphere and ocean. These changes opened the door for larger, more energy-hungry organisms to evolve. With more oxygen came the potential for more complex biology. Cells could specialize, forming tissues and organs. Organisms could grow larger, communicate internally, and develop new forms of reproduction. The Ediacaran explosion was not a burst of speed, but a slow, sweeping expansion of possibility. It was life realizing it could be more than it had ever been. Some fossils from this time show signs of early symmetry, a key feature in modern animals. Others show patterns of growth that suggest internal coordination. There are even hints of primitive sensory systems, although no direct evidence of nerves or brains has been found. Still, these early forms were stepping stones. They set the stage for the animals that would come next. The Ediacaran period lasted for roughly 90 million years. Over that time, the diversity of forms increased. New body plans emerged. Organisms became taller, wider, and more specialized. But toward the end of the period, many of these creatures vanished. They were replaced by more active, mobile life during the Cambrian explosion, when predators, shells, and rapid evolution transformed the biosphere again. Some scientists debate whether the Ediacaran organisms were direct ancestors of modern animals or a separate evolutionary branch that ultimately went extinct. Either way, they were a breakthrough. The first evidence that life had moved beyond the single cell. They proved that complexity could emerge, survive, and shape the world in new ways. The Ediacaran explosion reminds us that recovery from catastrophe is not just possible, but often transformative. Snowball Earth nearly ended life. Yet what followed was a flowering of biology, a quiet revolution in the oceans. These soft-bodied pioneers laid the groundwork for the rich ecosystems that would come later. Forests, fish, mammals, and even humans trace their history back to this moment. From a planet once locked in ice, life emerged, not weakened, but awakened, and in the quiet seas of the Ediacaran, the future began to take shape. Snowball Earth is more than a frozen chapter in the story of our planet. It is a turning point, a moment when the planet nearly lost everything, only to come back stronger, more diverse, and more complex than ever before. Its legacy is not just written in rocks or hidden in fossils. It lives in the structure of life itself, in the way the Earth breathes, evolves, and adapts. Before Snowball Earth, the biosphere was simple. Life was small, flat, and mostly passive. Oxygen levels were low. Ecosystems were thin. The evolutionary pace was slow. But after the freeze, everything changed. Snowball Earth acted like a crucible, stripping the planet down to its bare essentials and testing the limits of survival. What endured was not just life, but the potential for life to grow in new and unimaginable directions. The return of warmth and the rebirth of the oceans created new ecological spaces. Oxygen levels rose, energy flowed more freely, and with it, evolution accelerated. The first multicellular organisms appeared. The foundations for animals, tissues, and eventually complex nervous systems were laid. The snowball did not destroy life. It prepared it for transformation. Its legacy is also found in Earth's climate system. The snowball events revealed just how sensitive the planet is to small shifts in atmospheric gases, solar input, and surface reflectivity. The ice albedo feedback, which locked Earth in deep freeze, showed that even slow changes in carbon dioxide levels could tip the planet into extremes. This understanding shapes how scientists study modern climate change. It serves as a warning that Earth's balance can be lost more easily than we might think. The geological record of Snowball Earth has taught scientists how to read the signs of global catastrophe. Glacial deposits near the equator, cap carbonates laid down in sudden, massive floods, isotopic signatures that reveal a planet recovering from stasis. These clues have become tools to understand not just the past, but the future. They show how Earth's systems can collapse and restart, how life can pause, endure, and begin again. Snowball Earth also forces us to ask deeper questions. Why did life survive? How did it find shelter in such a hostile world? And what would have happened if it hadn't? If the ice had never melted? If the carbon dioxide had not built up? If the volcanoes had gone silent? Earth might have remained a frozen orb drifting through space, lifeless and still. But that is not what happened. Instead, life adapted. It found warmth in the deep ocean. It sheltered in meltwater pools. It evolved new ways to survive without sunlight. And when the ice retreated, it was ready. Snowball Earth showed that life is not easily defeated. Even in its most primitive forms, it is persistent, flexible, and full of potential. This event also shaped the direction of biological history. Some scientists believe that without Snowball Earth, complex life might have taken much longer to evolve, or may never have evolved at all. The extreme conditions may have acted as a filter, removing fragile forms and selecting for those that could adapt to stress. The genetic innovations required to survive Snowball Earth may have later enabled the rise of animals, mobility, and intelligence. In this way, Snowball Earth is not just a story of cold, it is a story of origin, a test that shaped the future, a moment of transformation hidden beneath ice and silence. We walk on a planet that once nearly died, but from that near death came something extraordinary. Snowball Earth reminds us that destruction can lead to creation, that collapse can lead to renewal, and that the most extreme moments in history often leave the deepest marks. The Snowball Earth theory is bold. It paints a picture of an entire planet locked in ice from pole to pole for millions of years. It explains strange geological formations, dramatic shifts in climate, and the sudden rise of complex life, but not everyone agrees with every part of the story. Even as evidence mounts, some scientists question the full scope of the theory. They ask whether the Earth really froze completely, or if a less extreme version of the event might be more accurate. One of the most debated questions is whether the oceans were entirely sealed in ice. The classic snowball model suggests that even the equator was covered by thick, permanent ice, with no open water anywhere on the surface. This would have shut down photosynthesis in most parts of the ocean and left only deep-sea vents and isolated cracks as possible refuges for life. But some researchers argue that this level of freezing would have been too extreme. They point out that life not only survived the snowball period, but later exploded into diversity. If the oceans had been completely frozen, it's unclear how enough life could have survived to fuel such a rebound. Instead, they propose a modified version of the theory known as the slushball Earth. In the slushball model, much of the planet was still frozen, but thin equatorial ice or isolated open patches of water remained. These ice-free zones would have allowed some light to reach the ocean surface, keeping small pockets of photosynthesis going. This version would still explain the glacial deposits found at low latitudes, but it offers a more forgiving environment for survival. Others question the duration of the snowball events. Some estimates place the Sturtian glaciation at over 50 million years, but alternative interpretations suggest there may have been breaks in the freezing, periods of partial thawing or regional melting, that don't show up clearly in the rock record. These interruptions would have changed the experience of life on Earth during that time, offering brief windows of light and warmth. There are also debates about the cause of the snowball state. While most scientists agree that a drop in atmospheric carbon dioxide and a rise in Earth's reflectivity played a role, some suggest that large-scale biological changes triggered the cooling. The rise of photosynthetic organisms before the glaciation could have pulled too much carbon dioxide from the atmosphere, weakening the greenhouse effect and making the planet vulnerable to ice growth. Others look to tectonics. The movement of continents into equatorial regions might have increased weathering and carbon drawdown. Or perhaps volcanic eruptions filled the sky with particles that temporarily cooled the planet, tipping it into a frozen state. There is no single answer, only a network of possible triggers acting together over time. Even the evidence used to support Snowball Earth is open to interpretation. Cap carbonates are often cited as proof of a sudden warming event, but their formation could also be explained by other geochemical processes. Glacial deposits near the equator seem convincing, but determining the exact position of ancient continents is not always precise. These controversies do not mean the theory is wrong. They mean that the story is complex. Science is a process of constant questioning, testing, and refining. The Snowball Earth theory has evolved since it was first proposed. New discoveries continue to shape it, and alternative ideas keep the conversation alive. What matters is that all of these perspectives agree on one thing. Earth experienced a period of extreme glaciation during the Neo-Proterozoic era. The planet changed, life struggled, and the aftermath was transformative. Whether it was a complete snowball or a slushy, partially frozen world, the impact was profound. Controversies remind us that the past is never fully settled. It is a puzzle, built piece by piece, from evidence scattered across the globe. And sometimes, the disagreements are what lead us to the deepest truths. While the traditional Snowball Earth theory imagines a planet locked in complete ice from pole to pole, not all scientists agree with that picture. Some believe that Earth may not have frozen entirely. Instead, they propose a slightly less extreme version of events, known as Slushball Earth. This model still describes a world in deep freeze, but with a few critical differences that would change how life survived and how the planet eventually thawed. The Slushball Earth hypothesis suggests that although most of the planet was covered in ice, some parts of the equator remained partially open or covered only by thin, permeable ice. These regions might have allowed a limited exchange of sunlight, gases, and nutrients, keeping small pockets of photosynthesis and ocean circulation alive. The rest of the world was still gripped by glaciers, but life in these rare equatorial refuges may have continued with a little more stability than the snowball model allows. The key argument for Slushball Earth comes from the survival of photosynthetic organisms. If the planet had been completely frozen, light would not have reached the upper layers of the ocean. Photosynthesis would have shut down almost everywhere. Oxygen levels would have collapsed, and recovery might have taken much longer. But if even small patches of ocean remained open or covered by thin, translucent ice, sunlight could have filtered through, microorganisms could have continued producing oxygen, and ecosystems could have persisted, barely, in these isolated zones. Evidence for slushball conditions can be found by looking at modern analogues today. In Antarctica and the Arctic, sea ice forms each year. Even during the coldest winters, some parts of the ocean remain partially open, driven by wind, currents, and temperature differences. Thin ice allows light to penetrate. Cryoconite holes and polynyas, natural ice openings, provide access to the atmosphere. Photosynthetic life continues in these harsh environments, proving that life does not need warmth, only opportunity. The slushball model also explains how Earth might have escaped from the glaciation more gradually. In a fully frozen world, greenhouse gases would need to build up to extreme levels before melting could begin. But in a slush ball scenario, where parts of the ocean remain active, even moderate increases in carbon dioxide might start the thaw. This would lead to a faster and more stable transition from cold to warm. Some rock evidence may also support this model. Certain sedimentary structures found in ancient marine rocks suggest that there was some movement of water beneath the ice. Ripple marks, microbial mats, and signs of weak currents point to at least some open or semi-open ocean conditions. These features challenge the idea of a planet completely locked in silence and stillness. The slush ball theory is not meant to replace the snowball model entirely. Instead, it offers a more nuanced version of the story, one where the Earth came close to full glaciation, but never crossed the final threshold. One where life was barely hanging on, not completely buried. And one where the planet was cold, but not entirely lifeless. This idea also fits with what we now understand about climate dynamics. Complete global freezing is rare and difficult to achieve. A near-complete freeze, on the other hand, is more likely. Small amounts of open water at the equator might have been enough to prevent total shutdown, and those small amounts could have made all the difference. The slush ball model reminds us that in the study of ancient Earth, absolutes are rare. Nature rarely operates in extremes without exceptions. And in the cracks between ice sheets and glaciers, life may have continued its quiet work, waiting for the sun to return. The atmosphere is not just a layer of gas wrapped around the planet. It is a dynamic system, constantly influenced by life, geology, and climate. And during Snowball Earth, this system was tested like never before. The deep freeze changed not only the surface of the world, but also the air above it. And when the thaw came, the atmosphere was never the same again. Before Snowball Earth, the composition of the atmosphere was very different from what we breathe today. Oxygen levels were low, carbon dioxide levels were higher, and other gases like methane played a more significant role. Life was mostly microbial, and the balance between gas release and gas absorption was slow and steady. But when the planet began to freeze, everything changed. As ice spread across the continents and sealed the oceans, many of the processes that regulate atmospheric gases were disrupted. Chemical weathering, the process by which carbon dioxide is removed from the atmosphere through interactions with rock, essentially stopped. With land buried under glaciers and rainfall greatly reduced, the natural removal of carbon dioxide came to a halt. Meanwhile, volcanoes continued to erupt. Deep beneath the ice, they released carbon dioxide into the atmosphere, slowly but continuously. Normally, this carbon dioxide would be balanced by weathering and biological activity, but with those systems frozen or slowed, the gas began to build up in the air. Over millions of years, carbon dioxide levels reached levels far beyond anything seen before. This buildup of greenhouse gases eventually became strong enough to end the snowball state. The atmosphere, thick with carbon dioxide, trapped more and more heat. Temperatures rose, ice melted, and the cycle reversed. But the story doesn't end with melting glaciers. The changes to the atmosphere were just beginning. As the ice retreated, newly exposed land was subject to intense chemical weathering. The warm, wet conditions after the thaw accelerated the breakdown of rock, pulling carbon dioxide out of the air at an incredible rate. This rapid weathering led to a crash in carbon dioxide levels, cooling the planet again and helping to stabilize the climate over the long term. The oxygen levels in the atmosphere also changed. During the snowball period, photosynthesis slowed dramatically. With sunlight blocked by ice and photosynthetic organisms buried or isolated, oxygen production dropped. This likely led to lower oxygen levels in both the atmosphere and oceans, contributing to mass die-offs and reduced biological activity. But after the thaw, photosynthesis returned, and it returned with force. Blooms of algae and cyanobacteria filled the newly open oceans, pumping oxygen back into the environment. Over time, this oxygen built up in the atmosphere, making it possible for larger and more complex organisms to evolve. The rise in atmospheric oxygen is closely linked to the appearance of multicellular life, and may not have been possible without the environmental reset caused by Snowball Earth. The chemical signatures of this transition are preserved in ancient rocks. Changes in carbon and sulfur isotopes reveal massive swings in atmospheric composition. The presence of banded iron formations during the snowball events shows that the oceans became anoxic, lacking oxygen and rich in dissolved iron. These conditions reversed after the thaw, indicating that the atmosphere and ocean chemistry were recovering together. Snowball Earth also altered the long-term carbon cycle. The extreme fluctuations in greenhouse gas levels helped shape the way Earth responds to climate stress today. The balance between volcanic emissions, weathering, and biological activity became more sensitive. The atmosphere learned how to recover from collapse, but it also became more responsive to disruption. In a sense, Snowball Earth recalibrated the atmosphere. It pushed the system to its limits, then allowed it to rebuild with new rules. The rise of oxygen, the decline of extreme carbon dioxide, and the formation of a more stable climate system all trace back to this frozen chapter in Earth's past. The air we breathe today, rich in oxygen, balanced in carbon, and protective of life, is partly the result of that long global freeze. Snowball Earth did not just change the surface, it changed the sky. And through that change, it made the future possible. It is one of the most haunting questions raised by the Snowball Earth theory. If our planet once froze from pole to pole, could it happen again? Could the systems that failed before collapse once more, plunging the world into another deep and deadly freeze? The answer is complex, but it begins with a truth that has always shaped Earth's history: the climate is not fixed. It changes, and under the right conditions, it can change dramatically. To understand whether Snowball Earth could return, we must first ask what made it possible the first time. The planet back then was different in many ways. The sun was weaker. Land masses were positioned differently, with large continents near the equator that increased weathering and helped pull carbon dioxide from the air. Life was simpler, and ecosystems were fragile. All of these factors made the planet more vulnerable to collapse. Today, things have changed. The sun is brighter. Plate tectonics has shifted the continents into a different configuration, and the biosphere is more robust. Forests, oceans, and soils work constantly to regulate carbon levels. Animals and plants drive complex feedback loops that help stabilize the climate. On top of that, human activity now influences the atmosphere in ways that no ancient process ever did. In the modern world, the climate threat is not extreme cooling but rapid warming. Burning fossil fuels has released vast amounts of carbon dioxide into the atmosphere, increasing the greenhouse effect and raising global temperatures. This trend is moving us away from the conditions that triggered Snowball Earth. Instead of a freezing planet, we now face the danger of rising seas, heat waves, and ecosystem collapse caused by too much warmth. Yet the possibility of global freezing is not entirely off the table. If, far into the future, carbon dioxide levels were somehow reduced drastically through natural processes, technological interventions, or unforeseen events, Earth could begin to cool again. If that cooling reached a tipping point and ice spread across the continents, the albedo effect could trigger a feedback loop, similar to the one that caused Snowball Earth in the past. However, scientists believe that a true snowball scenario is unlikely under current conditions. It would require a massive, sustained drop in greenhouse gases, combined with specific alignments of the continents and orbital factors that do not currently exist. And even if some glaciation were to occur, the presence of forests, diverse ecosystems, and human influence would all act to resist total planetary freezing. Some researchers have looked into the possibility of deliberate climate engineering artificially cooling the planet to counteract global warming. While these ideas are controversial, they show that humanity now has the power to influence the climate on a scale once reserved for volcanoes and continental shifts. This power comes with responsibility, because while it may not cause a new Snowball Earth, it could still push the climate into dangerous and unpredictable territory. Snowball Earth is not a prediction of our future. It is a warning from our past. It shows that Earth's systems are interconnected, fragile, and capable of tipping into extreme states. It reminds us that stability is never guaranteed, and that survival, for life and civilization alike, depends on understanding the forces that shape the planet. In that sense, Snowball Earth could happen again, not in the same way, but in spirit. A sudden, irreversible change brought on by slow, invisible shifts. Whether that change leads to fire or ice depends on the choices made now. The climate is still a system of balance, and history proves that when that balance is lost, the consequences are global. When Earth froze, it came closer to silence than ever before. Light faded, the oceans froze, the air thinned, the surface became a desert of ice, and yet, beneath all of it, life endured. Not loudly, not confidently, but quietly, patiently, hidden in cracks, clinging to vents, suspended in film-thin layers of water beneath the glaciers. In that stillness, life waited. What the story of Snowball Earth reveals more than anything is the resilience of life. It shows that survival is not always about strength. Sometimes, it is about the ability to pause, to adapt, to find warmth in the coldest corners, to keep going when everything else stops. This resilience is not dramatic. It does not roar or shine. It persists. It resists extinction by shrinking, folding in, and protecting itself until conditions return. And when they do, life does not merely recover, it expands, it transforms, it becomes something greater. After the snowball thawed, life emerged not broken, but reborn. New forms appeared, oxygen levels climbed, complexity evolved, and from that moment forward, the pace of evolution changed forever. What had once been a planet of microbes became a world of multicellular organisms, tissues, nervous systems, and eventually minds that could wonder about their own past. Snowball Earth is a story of catastrophe, but it is also a story of second chances, of the fine line between destruction and creation. It reminds us that even in the worst imaginable conditions, life can continue. And not just continue, but prepare for its next great leap. This history holds meaning for today, because we too live in a time of planetary change. Our atmosphere is shifting, our ecosystems are under pressure, and our choices will shape what comes next. The lesson from Snowball Earth is not that the planet is fragile, it is that the balance can be lost. And when it is, returning to stability takes time, sacrifice, and persistence. But if microbes can survive under kilometers of ice, if life can wait for millions of years beneath a frozen ocean, then we know that life itself is more durable than we often believe. It has endured fire, impact, ice, and flood, and every time, it has found a way to begin again. The story of Snowball Earth is not just about the past. It is about the strength hidden in small things, about the tenacity of life in the face of global collapse, and about the beauty that can follow even the longest darkness. Earth survived its coldest hour, and in doing so, it became the world we know today.